So I'm going to go over how to design a transformer. This is very basics. We're going to start, and suppose we want to design a transformer for a 50 hertz 240 volt system. So let's write down what we know. We know that its voltage is 240 volts, and we're going to let this be RMS, and we're going to let it be sinusoidal steady state. And we know that the frequency is 240 volts. 50 hertz. So let this be, for example, maybe for a transformer that you're going to use on the mains in Europe. So we want to, this is the primary voltage, and we want to build a step-down transformer. So we want the voltage on the secondary to be, let's say, 24 volts. RMS, and again, this will be sinusoidal steady state. So where do you start? You're not going to go to Ace Hardware and buy one of these things, so maybe you can go to DigiKey and find one, but you're probably going to end up having to get it custom or maybe make it yourself. So let's start also and say how much power we need to deliver on the secondary. Maybe we need 200 watts or 400 watts or 800 watts, so why don't we do 400 watts. So power, output, I'm going to call it 400. Let's be more general, we'll say 400 volt amps, because this allows the load to be not a resistor. It could be, for example, a motor or something like that. So the output current then is going to be simply 400 volt amps divided by 24 volts. It's going to yield, after doing a bit of arithmetic, so I'm going to get my calculator, 400 divided by 24. So that's going to be 16.67 amps. And that will also be RMS, and it will be sinusoidal steady state. Okay, so where do we start? Well, let's start with an imaginary transformer, which will use a core. So we use a core because the magnetic core is a good conductor of magnetic flux. So let's draw a core here. It's going to be a cartoon, but that's okay. So we have a core here. We'll let this be, for example, a laminated steel core, and it has some cross-sectional area like so. Okay. So we're going to have coils on this thing, right? Transformers have coils, so let's put a primary coil on here. Some number of turns. One of the first things we will do is compute how many turns are required. So this will be NP, will be the number of turns on the primary. So over here, we'll write NP equals number of turns on primary. How do you know how many to put? Can you put one turn? Do you need 100 turns? Do you need 1,000 turns? Well, I'm going to show you how to calculate that. And then we also know we're driving this with a voltage source, because I said it was going to be for use on the mains, which of course you're not actually going to plug this into the mains if you don't know what you're doing, because that could be fatal and lethal. So this is just an academic exercise. So we know that this is 240 volts RMS steady state. We know that there's a current here, like primary. Alright, and we know that the frequency is 50 hertz. So when you have a coil of wire and you run a current through it, you produce magnetic flux. And when the coil of wire is wrapped around a high permeability core, such as an iron core, a fair assumption is that all of the flux that you create is contained within the core. Now that's an approximation. It's a reasonable approximation if the core is highly permeable. So permeability is a measure of the ability of a material to conduct magnetic fields or magnetic flux. So iron has a high permeability. Air has a permeability equal to that of approximately a vacuum, which is quite low. So materials may have a permeability of 10,000 times higher than air. So it's a good assumption that all of the flux is in the core. So let this blue arrow represent the flux. And we'll give that a symbol, phi. So come back over here. Capital Phi equals flux. And it has units of Webers. So it's really, it's like the number of lines of flux contained within something. Now, something else that we'll notice about this is that we have a coil of wire, and it's wrapped around a core, and there's current running through the wire, so that's creating flux. So inductance is another thing that's related to transformers, highly related. Many engineers also don't have a good understanding of what that is. So inductance is, it's defined as the flux created by the coil, or coupled to the coil, but really it's created by the coil, per amp driven through that coil. Alternatively, it could be the amps produced in a coil for the flux in a coil, but it's really it's just the flux in the created divided by the number of amps. So it's Webers per ampere. Webers per ampere. Okay? And of course, this has a unit of henries, which we all know. So, henries. The core has a geometry. So, permeability is a material property, but the core also it has a geometry. So, in this particular case, I said, oh yeah, let me say that this is an iron core or steel, laminated steel. Okay, which is it's like iron, but it's laminated so that eddy currents are kept down, which is a secondary effect. But you can imagine that this is just a bunch of really thin pieces of steel just kind of stacked up on each other and glued together, and they might be 14 thousandths of an inch thick, for example. But that's laminated steel, and it has a cross-sectional area. Okay, let's call it 10 centimeters by 10 centimeters. I'm just making that up. It's not a particular value. In general, you'll have to solve for what cross-sectional area your device needs. We'll go through what the trade-offs are at different cross-sectional areas. So, the cross-sectional area of the core is then A, and it's really effective. A effective equals cross-sectional area of, and in this case it's the core, but in general it's the flux path of the magnetic flux path. Oh, if I could spell. Magnetic flux path. Now, we said that it was a good approximation that all of the flux was contained in the core because the core has such a high relative permeability compared to air. So in this case, the effective area is the area of the core. But also note that because it's a laminated core, some of that cross-sectional area is taken up by glue. In this case, we'll assume it's ideal and that there's no glue in there. So we'll actually say, that it's 10 centimeters by 10 centimeters. And so that's going to, I'll put it down here. That will equal 0.01 meters squared. And that's another thing. I use SI units, so you're not going to hear Gauss out of me, or Gilberts or anything crazy like that. Okay, so that's the area, and so we have a certain amount of flux, phi, and we have a certain amount of area. So if we were to say, what is the flux per unit of area, we would have what's called the flux density. So B is the symbol for that. It's flux density, magnetic flux density, and this has units of Webers per meter squared. All right? And the name given to this unit of Webers per meter squared is Tesla, after the one and only Nikola Tesla. Okay, so flux density is Webers per meter squared. Now, it would be nice if materials could conduct an infinite amount of flux, but it turns out that you can only cram so much flux into a geometric core shape, where you can only get so much flux in here before you saturate the core. So eventually what will happen is you'll have so much flux in here that it'll be full. And if you try to add more flux, it won't be contained within the material anymore. It will just be totally full. And once that happens, that's called saturation. So there's a limit to the amount of flux you can get in a core. And in general, there's a limit to the amount of flux density you can have in a material before the material saturates. And what that really means is, I mean, we could still cram more and more flux into there, but if you were to imagine inside of this core material, if we were to just look at a little bitty volume of the core material here, so we're zooming in like, I don't know, a lot. This is an approximation. So inside of here, you know, you have all of these little magnetic domains. This isn't flux, it's just a gross approximation for what's happening inside the core material. You have all these little magnetic domains, and they're all random for one of these magnetic materials that you use to make transformers out. So they all point in different random directions. But when you run a current through the coil, that's over here somewhere, so you have this coil over here somewhere that's connected to your transformer, and this is just a little volume section of that transformer. All of the magnetic domains begin to line up, and so that's what causes the material to conduct the magnetic flux so well, is that it has these little magnetic domains that all line up inside. But once all those magnetic domains are lined up in the same direction, there's no more of them to line up in that direction. So you could add more and more current, but there's no more domains left to line up. That's saturation. So what happens is that the relative permeability of the core starts to look like that of air. It goes down. So what we have to do as the transformer designer is make sure that we don't use up all of these magnetic domains and line them all up and then continue adding current, because then we will no longer have magnetic domains lining up, and the system will no longer be linear, and the currents will go through the roof for any particular applied voltage, and it gets ugly very quickly. So a material property is that you can only have a certain amount of flux density in that material before it saturates, and we call that value Vsat. So we have Vsat equals max flux density that you can have. Max flux density before the material saturates. Again, that's just like a gross approximation of what's really happening. You could get down into spins and quantum mechanics and all kinds of things, but at a higher abstraction, that's a good enough approximation for making 50 hertz, 60 hertz, 1000 hertz transformers, things of that nature, and it explains the phenomena well enough. So we have to make sure that we don't saturate the core. So different materials have different saturation flux densities. For laminated steel up here, Bsat is going to be equal to, maybe Bsat is 2 Teslas. So we'll say it's approximately 2 Teslas, and that's when all those magnetic domains are lined up. But we don't want to be close to the edge. We want some margin. So for in this case, let's choose 1.5 Teslas as the maximum flux density that we want to allow our core to operate. That leaves us a little margin in case we're not really in sinusoidal steady state, in case there's some noise on the line or something like that. So we'll choose 1.5 Teslas. All right, so what are we trying to do again? We are trying to calculate and understand how to calculate the number of turns required on the primary of our transformer here to make sure that the flux density that occurs inside the core does not exceed the saturation flux density, given the core material, the core geometry, specifically its cross-sectional area, the voltage we're applying, and the frequency that we're operating at. So I'm going to repeat that. We are trying to calculate the number of turns required on the primary of this transformer, given the transformer material flux density maximum, or saturation flux density, the core geometry, specifically the cross-sectional area, the applied voltage, and the frequency. So we need an expression that relates those things. So I'm going to do this. Let's pick a different color here. How about purple? So need expression to relate V primary. Again, this is RMS, sinusoidal steady state. The frequency, this is in hertz, or per seconds, or cycles per second, but per seconds. The cross-sectional area, the effective cross-sectional AEFF, effective, this is going to be in meters squared. Vsat, or the maximum flux density that we want the core to operate at. And in this case, the units is Teslas, or Webers per meter squared. And of course, in this case, I said we were going to be using 1.5 Teslas. And so what do we have? We have voltage, primary. Oh yeah, the last thing we're trying to actually solve for is N primary. Now, it doesn't have to be the primary per se, but that's the one we're trying. It could be any. It could be primary, secondary, tertiary. And this really is just number of turns. So we need an expression that relates all of these. Of course, we know all of these values. We know this is going to be 250 volts. This is going to be 50 hertz. We know this is 0.01 meters squared. Vsat is going to be 1.5. And N primary is the question mark. So we can use the formula known as the universal law of induction. So let's see here. Try to find my cursor. Related by universal law of induction. I don't know where I got that name, but I'm going to show you the equation and how to derive it and how to use it. Let's use another pretty color. How about orange? So the universal law of induction is as follows. V RMS sinusoidal steady state equals the factor 4.44 times B that you want. That's the flux density you want in the core. In this case, it's going to be Bsat. You may not want to design your core to run at that saturation flux density. You may want to run it at a lower flux density, but in general, we'll call it Bsat. I guess specifically we'll call it Bsat, but in general, it might just be B. So 4.44 B. Of course, that's in Teslas. Effective in meter area, effective in meters squared. Frequency in hertz times the number of turns. So there you go. This equation here does what we need. We know the RMS voltage. This is a constant. We know the saturation flux density, or the flux density we want the core to operate at. We know the effective cross-sectional area. We know the frequency, and we know the number of turns. One important thing to note about Bsat. This is Tesla peak, not RMS. It's peak. So when you're imagining all of those little domains, it's hard to imagine an RMS number of domains lining up. So we relate the RMS voltage to the peak flux density. That's an important thing to remember. So when we're talking about flux densities, we're talking about peak. When we're talking about voltages and sinusoidal steady state and currents, we're talking RMS. So where does this really come from? Well, let's write it slightly differently. So I can capture my cursor here. So let's write this differently. It's also equal to 2 pi f. So this is radians per second, right? Instead of, so this is the radian frequency times the effective area times the number of turns times the RMS flux density, BRMS. Okay, but how are we going to convert that RMS to peak? We are going to divide this by square root of 2. And so when we do that, this factor here is approximately 4.44. And that's where the 4.44 comes from. Approximately. So let's get little squiggles here. So why should you believe me that this equation is real and true? Let's go back to Faraday's law of induction. So Faraday's law of induction, okay, says induction, can't spell. Faraday's law of induction says that the voltage induced on a coil is equal to the negative time rate of change of the flux with respect to time. It should be dt. Okay? And it also has an n here for the number of turns. So voltage is minus the number of turns d phi dt. So V equals minus n d phi dt. So what do we want to do here? We want to solve for, convert this equation into this equation here. So how do we do that? So let's bring the dt over here and integrate. So the integral of V dt equals minus n integral of d phi. And of course, so this is volts, because that volts can come out. And this just becomes volt seconds. We can bring the n over here. We can also bring the minus over here. Equals the integral of d phi, which is, just integral of d phi is phi, right? So this is phi, which is the flux density. So we have volt seconds per turn is equal to the flux density. Now, volt seconds is something you will commonly hear in power electronics, and really all it is the flux density. So when we have volt seconds per turn equals the flux density. Interestingly, flux density, I'm sorry, not the flux density, this is the flux. Let's see if we can get some insight by looking into this equation back up here into this orange equation. So I think we can, if we say that, let me get a different color, maybe brown. Find my cursor again. These two terms here, their product, Webers per meter squared times effective area, that's going to result in, that is the flux. So that is phi, right? So we have voltage and we have flux and we have frequency. So if we divide through by these two terms, let me make some space here. Divide through by these terms. So we're going to bring frequency, flux density, and area over here. So V divided by B sat times A effective times frequency. This is simply V times these two are equal to flux, we just noted. So V over flux, and 1 over F is, so frequency is per cycle, so this is 1 over S, which of course we can move into the numerator just as S, and we are left with what equals some constant 4.44 times N, so we can call this proportional to N. So what do we see down here? We can swap these two, so we can have volts seconds per turn equals flux density. So this equation is consistent with Faraday's law, as we can see right here. These two expressions are consistent. Now you might ask about this minus sign. Recall that for sinusoidal steady state, a minus sign is referring to the phase. So there's a phase difference here, and this equation doesn't capture it, so this is more of just a magnitude, whereas this one includes magnitude and phase. But there you go. The universal law of induction, which is really voltage equals 4.44 BAFN, or BANF, however you want to write it, it is derived directly from Faraday's law of induction. So that's how you know you can believe it. So again, let's make some space down here, plug in the values that we have for flux density that we want to run our core at, the voltages that we want to run the core at, and see what kind of numbers we come up with for the number of turns needed for the primary. So we'll substitute these values here into this equation here. Let's rearrange the equation to solve for N. So N, which of course is the number of turns on the primary in this case, equals voltage, RMS sinusoidal steady state, divided by 4.44 BSAT A effective F. Okay? So plug those values in. Equals 250 volts, 4.44, 1.5 Teslas, 0.01 meters squared, 50 hertz, and I believe we get 77 turns. Let me just check on my fancy calculator. 250 divided by 4.44 times 1.5 times 0.01 times 50. Oh, I'm sorry, 240 volts, not 250 volts. Fix that. Oops, 240 volts. Plug that in again. 240 by 4. Okay, 72 turns, not 77 turns. So 72 turns. So that's the number of turns we need on the primary if we want to apply 240 volts RMS at 50 hertz to have 1.5 Teslas of flux density operating in the laminated steel core with a cross-sectional area of 10 centimeters by 10 centimeters. And let's calculate now the number of turns we need on the secondary. Of course, this is a transformer. Transformers have more than one coil on them, so let's get rid of this flux density lines up here and calculate the number of turns we need on the secondary. Let's make the secondary pink. So we'll go, this is a step down transformer, so presumably it will have fewer turns on the secondary than it does on the primary, which is the first thing to notice. We guess we can get all of this stuff out of here so we can calculate the number of turns on the secondary. So recall from EE 101 that number of turns on the primary divided by the number of turns on the secondary is equal to the voltage on the primary divided by the voltage on the secondary. This is of course idealized and assumes that all of the flux that's created by the primary is linked to the secondary, because recall, it's these lines of flux that are created by the primary, the current in the primary. These lines of flux have to couple through the secondary to actually induce the voltage on the secondary via transformer action. So this equation from EE 101 assumes that that's the case. It's a good approximation for most scenarios, especially at these low frequencies with iron cores. So we can rearrange this to solve for the number of turns needed on the secondary. So we have NPVS over VP equals number of turns on the secondary. Of course, we said over here that we wanted a 24 volts on the secondary. So let's plug in the numbers and chug. 72 volts on the primary. I'm sorry, 72 turns on the primary. 24 volts on the secondary. And we have 240 volts on the primary. So let's plug this into the calculator. 72 times 24 divided by 240 is equal to 7.2 turns on the secondary. Alright, go ahead and wind yourself 7.2 turns on this core. Well, you can't. Not easily. And fractional turns kind of just aren't allowed, because how do you get a partial turn? So you have a choice. You can either round this up and have greater than 24 volts, or you can round it down and have less than 24 volts, or you can find a number higher than 72 turns on the primary that's evenly divisible by 24. So maybe 8 turns on the secondary. So if we have 8 turns on the secondary times 24 volts, sorry, we have, let this be 8 turns. So what we really want is a turns ratio, N. We want it to be equal to 240 divided by 24 equals 10. That's what we want the turns ratio to be, to get exactly what we want. So because we can't get 7.2 turns on the secondary, we can round up to 8, and then we can resolve for the number of turns on the primary. So 8 times 10, 8 turns on the secondary times 10 turns as the turns ratio equals 80 turns on the primary. Now, we know that having 80 turns on the primary is enough to make sure that we don't exceed the 1.5 Teslas of flux density. In fact, increasing the number of turns will decrease the flux density, which in general isn't a bad thing. We just want to make sure we don't exceed 1.5, so adding more turns is okay. So 80 turns on the primary, 8 turns on the secondary, and there you go. We have solved for the number of turns needed for this transformer. So N secondary equals 8, and primary, this equals 80. Now, how are we going to go actually build this thing? You're going to walk into Ace Hardware, buy this transformer core, buy your wire. No, you're going to go and you're going to go on Mauser and you're going to look at the different transformer cores that are available to you, and you have to pick one that's available and will meet your needs. So perhaps you can't find one that's exactly 10 centimeters by 10 centimeters. Maybe you can find one that's 8 centimeters by 8 centimeters. In that case, it's close to this one. Rerun the numbers and you'll find that you need maybe 100 turns, or whatever the ratio is between 80 turns and the ratio of cross-sectional areas. But this gets you close. This gets you in the ballpark. Maybe you can find a core that's 10 centimeters by 10 centimeters. But maybe you know you have a core sitting on your shelf and you measure it and you know that it's 10 centimeters by 9 centimeters, and then you go through this calculation. I said that when we started this, I stated what I knew. The cross-sectional area I made up. But you may have to use whatever core you have. So you're going to go online and you're going to find your core and you're going to find your wire. So let's talk about cores, core types, when you would use certain cores, what their advantages and disadvantages are. So again, let's delete this and talk about different core types. So laminated steel, we are using that one for this one, and different cores will be used at different frequency ranges. So from say 1 hertz, whoops, wrong pen. So say from 1 hertz to somewhere around 400 hertz, maybe higher. These are gross approximations. You might use laminated steel with a BSAT of, maybe between 1.5 and 2 Teslas, somewhere in there, 1.5 or 2 Teslas, depending on how much you want to run through. The closer you get to 2, the less linear your transformer will behave in terms of the current needed to excite the transformer. So I like to run mine a little lower, but it can be optimized, and you can go up to 2. Like I said, these cores are laminated, so that's to help with eddy currents. So typically you'll be able to find these cores maybe with 14, well, we call it 014, 0.014 inch thickness, and that's pretty standard. You can get a little thinner. You can get half that thickness, so you can get 7 thousandths. These are also measured in gauges sometimes, so there's a lot of lingo out there, unfortunately, which is another reason why magnetics is difficult to learn. But you'll go with thinner laminations for higher frequencies when using steel. But you have to understand that, when you go thinner, you need more glue layers, so the effective cross-sectional area goes down. So you might look at, for example, Edcore. It's a brand that has many laminated steel cores, and they're good, approximately that frequency range. If you wanted to go up to a kilohertz, it'd probably work. It would just be a little more lossy, that's all. So then you might want to go from, say, 400 hertz to, say, maybe 10 kilohertz, maybe higher. Again, these are gross approximations. In this case, I would be looking at super thin cut steel laminated, cut steel amorphous cores. So these are super thin cores. So this might be something like AMCC Powerlight. These are trade names. This is made by Hitachi, but you can buy them all over. AMCC Powerlight. You can get C cores. That's just the shape of the core. These have flux densities of about 1.2 Teslas. That's for BSAT. And these are really good for this frequency range. They have low losses. They're amorphous, which means that they don't really have well-defined crystal structure, and those little magnetic domains really aren't there. So there's a lot less energy needed to flip those domains back and forth because they're so super small or even absent that it's one of the mechanisms for power loss in the transformer is dramatically reduced. Again, you can get these from all over, but I guess just search AMCC Powerlight cores. Bridgeport Magnetic sells them. There's some off-brands, but that's the trade name. Then you might want to go from, say, 4 kilohertz to maybe 100 kilohertz. And in this frequency regime, you're going to be using, especially at the higher end, maybe down at the lower end too, but any lower than 4 kilohertz, you're not going to want to use this. But definitely above 10 kilohertz, or especially above 20 kilohertz, you're going to want to be using ferrite cores. So these are ceramics or glass type cores with manganese, and they have very low resistivity, so they're very low conductivity, high resistivity as a bulk of the bulk resistivity is high. So you have low eddy currents. They're not laminated, they're sintered just like any other ceramic and fired. You can get them in all kinds of shapes. The trade-off here is that they're low loss and they work really well at these high frequencies, but their BSATs are really low. So you might be talking about order magnitude, 3.5, 0.35 Teslas, or 350 milliteslas, something in that range. We'll look at the effect of these different cores on the transformer design. And then above 100 kilohertz, they have ferrites that are good up to a megahertz. There's different core materials, but you might even use these up to a megahertz. Above a megahertz, the transformer are very hard to design, and you end up using a different type of transformer that has a slightly different set of equations. But there's some applications between 4 kilohertz and 50 kilohertz where you might use a material which is powdered iron. powdered iron has a higher flux density, higher saturation flux density than the ferrites, but it has a lower permeability. So this might have a BSAT around a Tesla, but it's going to have a much lower permeability. So what that means is that to get, you'll need more turns to achieve the same inductance, or you will have a higher excitation current in your transformer. So that's a kind of a sampling of the cores you might get. These you might get from Magnetics. That's the name of the brand. Magnetics. These ferrites, maybe Ferox Cube. Elna, the vendor, where you can buy ferrites. Of course, you can look on DigiKey and Metals and the other big guys. So let's look at what's actually happening here, though, when you might choose a different core. So let's go back to the universal law of induction here and take a look. If your saturation, let's put this in terms of N again. N equals V over 4.44 BANF. So what do we see here? Different core materials have different BSATs. So if your BSAT is higher, then the number of turns is lower because BSAT's in the denominator. If the cross-sectional area of your core is higher, the number of turns you need is lower. If, sorry, I made a mistake. N does not appear twice in this expression. That is just an F. If frequency goes up, the number of turns goes down. So, you know, you have freedom to choose kind of, you know, what material you use and what saturation flux density it has, what the cross-sectional area of your core is. Maybe you have control over the frequency. Maybe you have control over the voltages. Frequently, you'll see switch mode power supplies using a higher frequency so that they have a fewer number of turns, or a lower cross-sectional area, or the product of the number of turns in the cross-sectional area is lower. Even though the materials have a lower flux density, you know, a maximum flux density, you could still maybe quintuple your frequency and get away with a smaller core. So if we were to build this example inductor out of ferrite instead of this laminated steel, we would end up with a transformer that had, you know, we'd be going from a saturation flux density of 1.5 to maybe 0.3. So we'd be, you know, at least a factor of, well, 4 or 5 times bigger than we would be for this core. So that's why ferrites aren't used at line frequency. Ferrites are used when you have a switching circuit chopping up the line frequency, so you can use a much smaller core. Airplanes historically used 400 hertz instead of using 60 or 50 hertz for the very reason that all of the distribution transformers inside the airplanes could be smaller if they used 50 hertz, and they didn't have to fly around all this steel, which eats up fuel. So you do have a lot of choices here, and I just wanted to kind of show how this expression gives some insight into what's going on here. So another thing we need to look at before we can really go and start buying the materials we need is we need to look at the wire that we can buy. So you don't build transformers with lamp cord, and you don't build transformers with just any old wire. Typically, you're going to use magnet wire, which is enameled copper. Occasionally, for some transformers, you might use aluminum, but typically, you're going to use enameled copper. And so, how much wire do you need? What size? Typically, you're going to go on, say, Mauser, and you're going to buy Essex brand because it's what's available. Sometimes there's many brands, but Essex brand seems to be in stock. You're going to buy them in a 14-pound spool. So if you go and you buy, 36 gauge wire at 14 pounds, it's going to be much longer than a 10 AWG is for a 14-pound spool. And they have different builds. So they have single, double, and triple build. So single is just one layer of varnish. So that means that it gets one layer of varnish put on it, or enamel, I should say, not varnish. This is enamel. Excuse me, enamel. This double build is going to have 2 layers. This is sometimes in industry nomenclature called heavy build. Again, a lot of lingo, which makes things hard. Triple is going to have 2 layers of varnish and then an additional layer of regular insulation, which may be enamel coated, enamel impregnated fiberglass or something else. For UL transformers, triple insulated is required if you are not going to isolate the whole circuit. But anyway, I typically use heavy build double. There's all different temperature ranges, which has more lingo. H is what I use. So I use heavy build H class, which I think is good for 240C. And again, that's what I can usually just find on Mauser, so that's what I buy. It's not cheap, but it's what I can buy and what I can get. Okay, so let's look at the power. We said we wanted to have 400 VA. Oops. I must have changed my brush size there. Stand by. So we have 400 VA, and we have it at 24 volts. So what's 400 divided by 24? It's going to be about 8 amps, right? 400 divided by 24. Oh, I'm sorry. It's going to be 16 amps. So I can design transformers, but I can't do arithmetic. 16.66 amps. So in this range, you're going to go look up the AWG wire tables. Maybe you're going to look at 12 AWG or 10 AWG, something like that. The ampacity tables aren't really meant for transformers. They're really meant for other cabinet wiring and things of that nature. So that's why transformers go on temperature rise. So we allow more losses in a transformer wire than we would in, say, a cabinet wire. So that's just a rough estimate. But essentially what's going to happen is you're going to build it and test it and make sure it doesn't get too hot. And then that's for the secondary. That's for secondary. For the primary, we have 400 VA. Whoops. 400 VA divided by 240 volts. So that is about 2. So just under 2 amps. So let's call it 2 amps to be conservative. So maybe you're looking at 18 gauge wire. Something like that. You can calculate the total length. 10 centimeters per side. So 40 centimeters per turn. You have 80 turns. 4 times 8 is going to be, whatever that comes out to be in length. So you can estimate the total length. You can estimate the DC resistance. In an AC circuit, you're going to have skin effect. These are things you should go look up. Skin effect. This is due to the fact that magnetic fields don't like to penetrate conductors, and the wire is actually a conductor, and it's in the presence of a magnetic field, and so that the current tends to run on the outer layer. So the skin effect is saying that the current is really running in this outer layer of the conductor and not the central part. And that's for frequencies where the skin depth is less than the radius of the conductor. So I'll go ahead and look that up. And the other one is proximity effect. And this one is due to the fact that you might have 2 wires laying next to each other, and the magnetic field from wire 1 is coupling to wire 2, because of course wire 1 has a magnetic field going around it. It's cutting across wire 2, which is excluding a part of wire 2, so current tends to crowd over here. So these two phenomena combined end up making it so that solid core magnet wire is not really very good at high frequencies. Say anything above a couple kilohertz, you're really going to lose a lot. You're going to have a lot higher resistance and a lot higher power loss. So you might use something called litz wire. Litz wire is more expensive and even more difficult to find than regular magnet wire, but it is available. I find that the best source is actually eBay, because minimum order quantities and long lead times make it hard to get anything less than $1,000 worth. But you can buy it on eBay. And that's something you might want to consider if you're doing anything above a few kilohertz. And the nice thing with litz wire is there's tables that tell you, for example, well, let me tell you what litz wire is. Litz wire is wire that's made of many strands of individually insulated wires, and they're randomly wound or twisted to offset both the skin effect and proximity effect. I forgot what I was going to say about litz wire, but there's different kinds, and you can buy them on eBay. For one example is I built a 25 kilohertz transformer with solid core magnet wire, and I measured an equivalent resistance on the primary of 4 ohms, and then I switched to litz wire, and I measured of the same cross-sectional copper area, and I measured a resistance at 25 kilohertz of 0.8 ohms. So over a factor of 4 improvement. But the way it's specified is you might have 105 strands of 36 AWG wire. So 105 strands of 36 AWG wire, where each of the 105 strands is individually insulated. And the tables available tell you that for frequencies from 20 kilohertz to say 30 kilohertz, 36 gauge wire is small enough that the skin depth is larger than the radius of the wire. So 105 turns of 36 gauge wire might be something like, this might be 16 AWG equivalent. But if you want to go higher in frequency than that, maybe you need 240 turns of 42 AWG or something like that. I'm making these numbers up, but the tables are available if you just search litz wire tables. This will still be a 16 AWG equivalent cable, but it's better for a higher frequency, maybe up to 50 kilohertz, because at those frequencies, 42 AWG wire is is smaller than the skin depth of the associated current. Anyway, I've hit an hour here in length, so I hope this was helpful, and I've gone through, again, the process, starting from scratch, of the very fundamental basics of producing a transformer. Thank you.